Welcome again. In this video, we are going to talk about the specification of of measurements for certain types of radiation. We understood now that the exposure, the equivalent dose, and the radiation absorbed dose kind of fail to specify that certain type of radiation. So in order to specify a certain type of radiation, we have to have something which is known as the quality factor, which is abbreviated by Q. Quality factor, in simple terms, represents the biological effects of each type of radiation. How much energy of that radiation is deposited into tissue. Whether all the energy is deposited into the tissue, partial deposition, or complete deposition. The quality factor, the X-ray and gamma rays, they have been given a quality factor 1. The fast neutrons, protons, and beta particles are given a quality factor 10, and the alpha particles are given a quality factor of 20. What does this mean? These are alpha particles and beta particles and gamma and X-ray photons. As you can see that alpha particles, they have a quality factor of 20. It means that when alpha particles interact with any material, in this issue it's been given like with paper, the alpha particles, they are going to deposit all their energy into that thin structure. It will stop it all. So the effect of alpha particle on that structure is very high. That's why it's given a high quantity factor. On the other hand, the beta particles and the fast neutrons and the protons, they do not deposit all their energy in paper here. They are going to deposit some of their energy, and some of the remaining particles will pass, and they will deposit the remainder of their energy into aluminum, for example. So their quality factor is 10. But X-ray has a low quality factor. Why? Because it can easily pass paper, so it's not going to deposit all its energy into paper, and then it has remaining energy to pass by aluminum, leaving some of its photons, giving its energy to aluminum, and then it fails. Most of the photons will fail to pass lead here because of the high atomic number and the energy. This is another issue, but we're talking about the quality factor here. So the quality factor of X-ray is relatively low, and it is given number 1. Let me put it in another way. Let's talk about light and X-ray. If I put my hands below a light, you'll see that light photons my hand will absorb all the light photons, remaining nothing will pass out of my hands. So the light photons, their quantity factor is high to my hand. While X-rays, some will be stopped, while others will pass out. This is pass away, out of my hand. This is how we record images. So the quality factor of X-ray is low. I think now this is a simpler representation of what quality factor means. So quality factors is the biological effect of radiation, how much radiation is deposited into a certain material. So the equivalent dose, which is the third way of measurement, how it is calculated. The equivalent dose equals radiation absorbed dose, which is measured by Grays, this is a generic type of radiation absorbed dose, does not specify any type of radiation. It's very general. So if you want to specify to a certain type of radiation, you have to multiply it by the quality factor of that radiation. So in order to calculate the equivalent dose, you have to know the radiation absorbed dose, and then you multiply it by Q of that energy, so you will get the equivalent dose of that radiation. Since the Q for X-ray is 1, then the equivalent dose equals radiation absorbed dose for gamma rays and X-rays. In other words, the equivalent dose, which is represented in sieverts, equals the radiation absorbed dose represented in grays. In other words, when we talk about radiation units for X-ray, gray and sievert are the same. The equivalent dose and the radiation absorbed dose is the same. Now let's come to the calculation of the effective dose. See, now we know in order to specify a certain type of radiation, we have to multiply the radiation absorbed dose. Its unit is gray. You have to multiply it by Q. But here you don't have the type of tissue that is being irradiated, which is another important issue. See, tissues react differently to radiation, to the ionizing radiation. They absorb the radiation. That means the photons, the X-ray photons, will give their energy to the cells, to the atoms of the cells. But which cells and which tissue? So each body tissue is affected differently by radiation. The effective dose, in order you have to calculate effective dose for the body, you have to measure, or it's a measure that allows the doses from different investigations of different parts of the body. Each tissue is affected differently by converting all the doses to an equivalent whole body dose. That is the dose for the RBCs, white BCs, muscles, fibers, fibroblasts, organs, and so on. So you calculate all of these in order that you have to have an equivalent whole body dose. Okay. In order to achieve this, as we know that tissues react differently to radiation. Okay, the radiosensitivity is different. Then we have to specify the radiosensitivity of tissues, and this is what is meant, or this is expressed by the tissue weighting factor, or the WT. WT measures the radiosensitivity, i.e., the risk of tissue being damaged by radiation. The higher the damage, the higher is the amount or the value of W. Mind you that W and Q are absolute values. They have no. It's not expressed by any other unit. So either we say Q and W. It's just numbers. Okay. So this table shows us the weighting factor or WT of different tissues. You see that for skin it's 0.01, which is equal to the bone surface, equal to brain, and equal to the salivary glands. The weighting factor of these different tissues, it means that their radiosensitivity, how much they are affected by radiation, is almost equal.